Welcome, physicists. It's Mr. Gopal here with an exciting lesson from our modern physics unit on the four forces. This is day 16 of unit 6, which is modern physics. We want to get to know the four fundamental forces. Now, I think I've said this before, but it bears repeating. When we go through the process of studying Regents Physics, it's an initial look at physics. And just like all of the other sciences at the high school level, it's more complicated than anything that you studied in middle school. However, it doesn't quite even begin to hint at the complexity that you would get if you studied undergraduate physics. And of course, even that pales in comparison to graduate physics. Now, the idea here with physics and really with all of the sciences is that you would continually return to the same topics as an undergraduate student and a graduate student, but the complexity would be layered up. And so we want to take our initial look at the four fundamental forces. Bear in mind, when I make this video or when you watch this video, you won't have all of your questions answered, but you will get a better snapshot about why things are the way they are. And I mean that not only at the level that you can see at this macroscopic level, but I mean it at the microscopic level down into the subatomic particles. So the purpose of this lesson is to be able to describe the four fundamental forces and what makes each one special, right? And we're going to kick off with a little bit of a review. So I'm going to answer the first and third questions first to give you a bit of a background here, and then we're going to talk about the second question as well as the fourth force, which is not present in these three questions, all right? Inside the nucleus of an atom, there are positively charged protons. What force did you learn about earlier this year, which makes two positive charges repel? Okay, and so a hint into how to answer this question is in the wording of the question itself. If we're talking about forces that would make charges repel, we were talking about the electrical force or the electrostatic force. The electrostatic force specifically makes like charges repel and opposite charges attract. Okay, and two protons obviously repelled. Now, I'm going to jump down to the third question. Protons also have mass, and we're going to take a look at the physics reference table to get a specific picture of their mass. What's the force that acts between any two objects with mass, which we spent the first half of this year talking about? Again, the question is worded very well. In order to activate that prior knowledge, this is a force that we talked about from the beginning of the year. This is the gravitational force. So gravitational force acts on any two objects with mass, irrespective of the distance between them. And so between these two forces that we've already studied, hopefully you do remember, but if you don't, I'm going to repeat it right now. The electrostatic force is much stronger than the gravitational force. And now that we know that, if we're thinking critically about the nucleus and the fact that many like charges, many protons are held together in the nucleus more and more for elements with higher atomic numbers, we have to think that there is another force involved in keeping them together. And so there's another force within the nucleus which prevents the protons from separating apart. What's the name of that force, which we learned about recently? This was covered in a recent lesson. It bears repeating, though, that this is the strong force. Strong force, in a nutshell, is responsible for holding particles together. And now, as you might assume, given that the electrostatic force is stronger than the gravitational force, the strong force is even stronger than the electrostatic force. All right, so we have these three forces, the weakest of which is gravity, the strongest of which is the strong force, and in between is the electrostatic force. Now, if we go on to the next slide, we want to talk about which one of these are attractive and which ones are repulsive. Now, we just answered that question, and that question was in the wording of the previous questions on the previous slide. The electrostatic force is obviously a repulsive force, given that we're talking about protons and protons have the same charge. Now, when it comes to the strong force, it's an attractive force. And of course, since protons have mass and they're separated by a short distance, the gravitational force between them is stronger than it is with many objects that we see separated by, some span of air, like my water bottle and my phone right here. Okay, they are much closer together. So the gravitational force is relatively strong there. Nonetheless, it is weaker than the electrostatic force. Again, the strong force is stronger than either of them. Now, a quick note on the weak force, all right? The weak force is a force that is responsible for nuclear decay, all right? So I'm going to summarize the weak force briefly right now. It is a mechanism of interaction between subatomic particles that's responsible for radioactive decay. If you recall from chemistry, radioactive decay of atoms is when we have a conversion from neutrons into protons, all right, which changes the element involved. And if you recall, there are different types of decay. There's alpha and beta decay, all right? But what you might remember from this breakdown, this radioactive decay in certain, in the nuclei of certain elements, is that it takes a tremendous amount of energy, all right? And so this helps us understand the reason why the weak force happens to be called the weak force, all right? The weak force is still stronger than gravity. Gravity is the weakest of the four, but it is weaker than the other three. So if I were to rank all of these from weakest to strongest, four forces are: one, gravitational force, that's the weakest. Two, the weak force, responsible for nuclear decay. Three, the electrostatic force. And four, the strong force. And isn't it something? It's highly valuable to us that the strongest of the four forces is the one that holds particles together. Thankfully, that is the case. Otherwise, we would live in a world where nothing is held together and things atomize and break apart all the time. So thank goodness for the weak, or for the strong force, sorry. Now, the final thing that I want to do is talk about how to calculate the magnitudes of electrical force and gravitational force on two protons in the nucleus, all right? So we've got a bunch of things in the reference table to help us make this calculation, all right? And I'm going to go through those things. All right, first thing that I'm going to do is I'm going to write out each of these formulas for us, all right? When it comes to electrostatic force between objects, we have this equation, which hopefully strikes you as familiar. So to calculate the electrostatic force between two objects, we need this. F sub E is going to equal K times Q1 times Q2, all divided by R squared. In this equation, Q1 and Q2 represent the charges of each of the objects. K is what we call our electrostatic constant. And then R is the distance between the objects, all right? So if we're calculating the electrostatic force between two protons, here's how we do it. We're going to jump to the reference table and find some valuable information. All right. The first thing that we want is the electrostatic constant. We can see it right here. K is equal to 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. All right. We know that Coulomb is our measure for electrical charge. All right. So we can write that down here. K K is equal to 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. All right, now we also need the charge of a proton. The charge of a proton is going to be 1.67 times 10 to the negative 27th kilograms. Oops, I'm sorry, that's the mass of the proton, which we're going to use in our following calculation. The charge of a proton is actually going to be equal to 1 elementary charge, which, as we can see right here, is 1.6 times 10 to the negative 19th coulombs. All right, and it's going to be positive because protons are positively charged. All right, so if I go back here, I could say that Q1 and Q2 are both equal to 1.6 times 10 to the negative 19th coulombs. All right. Finally, the distance. Now, they don't tell us the distance, but the way that we tend to observe the distance between subatomic particles in the nucleus is in distance called Fermi. All right, and a Fermi is 10 to the negative 15th meters. So we're talking about this microscopic amount of distance that we can't really see here. All right, I'm just going to write it out here. Our R is going to be 10 to the negative 15th meters. All right, and so if we plug all these things in, here's how we would calculate the electrostatic force between two protons in the nucleus. It's going to be equal to 8.99 times 10 to the 9th times 1.6 times 10 to the negative 19th. We're going to multiply that again. So I'm just going to say we're going to square that number, and then we're going to divide it by a Fermi, or 10 to the negative 15th meters squared. Okay, and if we do this calculation, I'm going to do it right now. I'd like you to do it along with me. All right, so plug in 8.99 times 10 to the 9th times 1.6, sorry, 1.6 times 10 to the negative 19th squared. That's going to equal roughly 2.3 times 10 to the negative 28th. And now we're going to divide that by 10 to the negative 15th squared, which ends up being 10 to the negative 30th power. And now that's going to give us a tremendous amount of force, given what we're studying is so microscopic. The electrostatic force you should have gotten is 230.144. And we're going to say that that roughly equals about 230 newtons. How do I know it's newtons? Well, if you look at our constant, that's a Newton meters squared per Coulomb squared. We have meters squared in the denominator, so the meters cancel. And then we also have Coulomb squared in the denominator of our K, but in the numerator of our Q1 and Q2. When we multiply coulombs by coulombs, we get Coulomb squared, so those cancel out, and that gives me newtons. Now this is how we calculate the force between two newtons. I'm sorry, I'm on the wrong slide. Leave that up for a second. Now I'm going to clear this, and let's do the force of gravity, just to compare it. So 230 newtons is our electrostatic force between those protons. Now let's calculate the force of gravity, the F sub g. And for this, we're going to use the formula that we used previously to calculate the gravitational force between objects on Earth. All right, and so capital G is our universal gravitational constant. If you look here, it's 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. So capital G equals 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. Now we need the mass of a proton. I cited it before incorrectly as the charge of a proton. If we look at the rest mass of the proton right here, scroll up so we can see that a little bit easier. We have 1.67 times 10 to the negative 27th kilograms. And that is our M1 and our M2. 1.67 times 10 to the negative 27th kilograms. So this has a tiny, tiny amount of mass. There are two of them. And then again, we're going to use the Fermi for our radius, and that is 10 to the negative 15th meters. That is our distance between these two. And so if I plug it all in, here's what it looks like. We're going to do one more calculation. Again, I can just take 1.67 times 10 to the negative 27th, and I can square it because I have two protons and they both have the same mass. And then I'm going to divide it by 10 to the negative 15th, negative 15th. But I'm squaring that. So it's really going to be divided by 10 to the negative 30th. So let me clear this. That's going to be 6.67 times 10 to the negative 11th times 1.67 times 10 to the negative 27th, all squared. That gives me a tiny, tiny number, 1.86 times 10 to the negative 64th, all right? Now I'm gonna divide that by 10 to the negative 30th. And this is what I get. And hopefully you can appreciate the massive difference between the magnitude of our electrostatic force between these two protons, which was 230 newtons. And this is the number that I calculated for the gravitational force. Okay, so in other words, we have a repulsive force of 230 newtons between these two protons. We have an attractive force from gravity due to gravitational force of 1.86 times 10 to the negative 34th newtons, a drop in the bucket comparatively. So we know the strong force has to be far stronger than the electrostatic force in order to make up for the shortfall with the force of gravity. And this is why protons do not separate. I hope that this was a good introduction to these three forces, not as much the weak force, but we will return to the weak force. And I hope it helped you understand how to use the reference table and make use of equations that we've already used in the electricity unit and throughout the first half during kinematics whenever we talked about gravitational force. So this has been a nice introduction to modern physics. I'll be back with more soon. I hope this was helpful, and I will see you soon.